multiplication of signed numbers and unsigned numbers, we are supposed to do that multiplication with the help of Booth algorithm. Why do we need to do this? Why do we need to use a Booth algorithm? Is that ALU? If you talk about the ALU cannot directly store any kind of negative numbers. It cannot store any kind of signed number. So in order to overcome that particular situation, we'll be using this Booth algorithms. Booth algorithms are mainly used for doing the multiplication of the signed numbers and also unsigned numbers. Usually in this particular PPT slides, probably I might be showing you both the positive numbers first, and if time permits, I'll go for the unsigned numbers also. That is called like negative and positive numbers, multiplication of two negative and positive numbers. So see now, this is the flowchart of the Booth algorithm. I hope you can see it clearly. First, I'll try to explain you how the Booth algorithm will be working, and later we'll try to see one example over here, and if time permits, we'll go for the chalk and board kind of lecture. So see first, if you're starting, you'll be having like there are like three address cells have been used over here in this particular Booth algorithms. The first one is called as an A. A is nothing else but it is called as an accumulator, where your data has been stored after doing some operations. So it is called as an accumulator. Accumulator. A is used accumulator, and Q minus 1. Q minus 1 is nothing else but if you are having a one memory cell of 4-bit, if it is a 4-bit, assume that if a memory cell is of 1, 0, and 1 and 0, if this is my 4-bit cell, assume this is my Q. Q is nothing else but we call it as an multiplier. In a multiplication, we know that we'll be having a multiplicand and also multiplier. If I'm trying to multiply 2 into 3, then I can call this 2 as on my multiplicand and 3 will be my multiplier. So now this Q is called as a multiplier. So this is Q0 and this will be my Q1. The one this is Q1 and this is my Q2, and ultimately it will be my Q3. So this is how the memory will be named depending upon the 4-bit numbers. So these are the memory locations. So Q0, Q1, Q2, and Q3. So this is Q0 is Q minus 1. If you can see over here, excuse me, I'll take a pointer over here now. So see now, this is Q minus 1. This Q minus 1 is nothing else but the one which is before or else on the right side of your Q0. So it is Q minus 1. Since already Q0 has started, Q0 is over here. The previous to that Q0 will be Q minus 1. Let that Q minus 1 is an 1-bit memory cell. It's a 1-bit memory cell, and that is been assigned to a value called as 0. It will be assigned to a value called as 0, and accumulator will be of a 4-bit memory cell, which will be assigned to a 0. It will be like 4 zeros will be assigned, and ultimately M is the multiplicand and Q is a multiplier, and N is a number of counts. N is a number of counts. So what does this number of counts denote over here? If I'm trying to multiply two 4-bit numbers, if I'm trying to multiply two 4-bit numbers, if it is 2, means what? Your value will be 0, 1, 0. I hope so. 4-bit 1 means this will be my 2, and for 3 it will be 0, 0, 0, 0, 1, and 1. So this will be my binary 2 and binary 3. So see now, I'm having two 4-bit numbers over here which are to be multiplied. I'm by using the Booth algorithm, I'll be doing a multiplication of binary multiplication will be done over here. So I'm trying to convert this decimal numbers into binary first. Then 2 is equal to 0, 0, 1, 0, and 3 equal to 0, 0, 1, 1. Then after that, if I want to multiply this one, then here count means count. It is been denoted as n. It means that if you are having the 4-bit numbers, if you are trying to multiply 4-bit numbers, then the number of iterations, the number of iterations or iterations which are possible in this particular Booth algorithm will be 4. It means that you will be working with this Booth algorithm in order to do this multiplication with respect to the 4 steps. You'll be working for the 4 step. The 4th step will be your final step to wind up that particular algorithm, and the last one which you get, that is your final answer. Okay, if you are trying to multiply two 8-bit numbers, if you're trying to multiply two 8-bit numbers, then what happens? Your final answer will be, you'll be having an iterations will be of 8 iterations, steps will be 8 steps in that Booth algorithm, and last after 8th step you'll be getting some data, and that data will be a product of that two numbers. So that is called as an n count. Count is nothing else but that is the n. So see now, let us now enter into the Booth algorithm. In this Booth algorithm, if I'm trying to do this particular operation, if I started my process at the first step, in the first step it is Q0 and Q minus 1. See now, if it is Q0 and Q minus 1, Q0 and Q minus 1, I'm talking about these two parts. If it is Q0 and Q minus 1, it is, there are two values have been given, 0 0 and 1 1 initially. If it is 0 0 and 1 1, whenever Q0 equal to 0 and Q minus 1 is equal to 0, then what happens? It goes to the arithmetic shift right will be taking place. Whenever the Q0 equal to 0 and Q minus 1 equal to 0, arithmetic shift right shift will be taking place, and after that you will be just doing the arithmetic right shift will be done over here. Similarly, it happens even for the 1 1. If Q0 equal to 1 and Q minus 1 equal to 1, the arithmetic right shift will be taking place. In the same way, whenever the Q0 equal to 1 and Q minus 1 equal to 0, let us see what happens. Whenever the Q0 is equal to 1 and Q minus 1 equal to 0, then what happens here? You'll be doing this subtraction kind of a operation will be done, where accumulator, the multiplicand will be subtracted from the accumulator. But initially as I told that in ALU, while studying the ALU, it's not like we will not be using any kind of subtractors, but you will be adding a minus kind of term to the another term. That's again, it's an addition only. If you're trying to subtract a minus m, if it is a minus m, means you're not actually doing a minus m. You're trying to add a plus minus of m. So that's what we'll be doing over here. Whenever it is 1 1 0, then you will be doing a minus m, and that whatever the answer you get, that will be stored in the 4-bit memory, which is called as an 4-bit memory cell, which is called as an accumulator. So this data will be stored over here in this particular accumulator. If it is 0 1, whenever it is 0 1, what happens here? If it is 0 1, then an addition operation will be done. In the addition operation, what you'll be doing? It's just addition of multiplicand and the accumulator value, which you find at the particular step, at the particular iteration step. So that is how it happens. And after that, once CNO, it is mandatory that whatever may be the operation, whatever may be the conditions over here, whether it is 0 0 1 0 1 1 1 0 or 0 1, ultimately after doing that particular operation, the mandatory operation is that right shift has to take place. Arithmetic right shift has to takes place for all the operations of all these 4 cases. For 1 1 case, 0 0 case, 1 0 case, or 0 1 case, ultimately the right shift operation has to take place. Whereas for this 1 1 and 0 0 case, directly the right shift operation will be taking place. But for this 1 0 and 0 1 case, these 2 operations have been done with respect to their values, and then after that one, the right shift will be taking place. And ultimately, the count will be counting the number of steps. If it is a 4-bit multiplication has been done, then after the 4 steps, you'll be ending this particular Booth algorithm. So see now, the same thing whatever I have explained is been given over here. We will use the Booth algorithm either or both numbers are negative. We'll use the Booth algorithm whenever one of the number is negative, or else either the number is negative, or else you can even use it for the signed number or unsigned numbers also in this way. So now in Booth algorithm, we look for the transition of 0 1 and 1 0. We look mainly for this transition of 0 1 and 1 0, and also we ignore the 0 0 and 1 0 sequence in our multiplier. Why? Because there will be no operation will be done. It is only no change will be done. It is only the arithmetic right shift will be taking place in this particular Booth algorithm. Let us see what happens here. The same thing we have just now seen. Compare the rightmost bit of the particular bit, there is a Q0, that is compared with the previous rightmost bit, that is Q minus 1. you will be always comparing these 2 bits in terms of 0 0 1 0 1 1 1 0 and 0 1. The initially this particular q minus 1 is initiated to the initialized to 0 if the sequence is 1 to 0. Whenever if its sequence is 1 to 0, 1 to 0. So see now, if it is 1 to 0, what is happening? Now in this case, it is happening a plus 1 should be added. So sequence is 1 to 0, it is a plus 1. Again, it is a 0. Sorry, if it is 0 to 1, it will be both will be added. If it is 1 to 0, it will be a minus 1. If the sequence is 0 0 or 1 1, we do not add or we do not subtract, but we will be doing only the right shift operation. Okay. So now after the each iteration, you will be doing the shift. Whatever may be the iteration, on after each iteration, you will be doing an arithmetic shift. Arithmetic shift, right shift is a mandatory kind of operation in this Booth algorithm. So see now, I have given here one example. In this one example, first, this is like we are trying to multiply two numbers where the two numbers are nothing else but 0 1 1. You can see over here now, as I told, where is my pen? Yeah. So see now, this is my first q. What is q? Q is called as a multiplier and m is called as a multiplicand. So these two numbers are to be multiplied. So first, the multiplying concept will be in this term. It is m cross q. M cross q means first we'll try to find it out what is that number. If it is m is 0 1 1 1, if it is m 0 1 1 1, it is nothing else but it is 7. It is 7. It is 7. You can see that how it is 7 means it is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. So all these are ones and this is 0. I need not take this. I need not consider this one. So 2 to the power of 2 is it is like 2 to the power of 3. 2 to the power of 2 to the power of 0, 2 to the power of 1, 2 to the power of 3. So now ultimately what you come across over here, this will be your final answer. So you'll get it as 7 over here. Then in this case, it is q equal to 0 0 1 1. In 0 0 1 1, this value will be equal to 3. 2 to the power of 0 is 1, 2 to the power of 1 is 2. 2 plus 1 is equal to 3. And here it is 2 to the power of 0 is 1, 2 to the power of 1 is 2. Again 2 to the power of 2 to the power of 1 is 2, 2 to the power of 2 is 4. So 4, 2 and 1, it will be 7. So ultimately you are multiplying the decimal number of 7 into 3. So you are supposed to get your answer that is equal to 21 should be your answer over here. So it is this should be your final answer, and that final answer should be in terms of your binary number. So see now, first what you're supposed to do, as I told, as per the Booth algorithm, first you're supposed to initialize your A. The 4-bit accumulator has to be initialized. I have initialized the 4-bit A, that is equal to 4-bit. So it is equal to 0 0 0. All 4 zeros have been initialized. And what is my Q? Q equal to, this is how the tabular column has to be made. First initializing of the values will be done. The Q is equal to, first A should be written, afterwards Q should be written, then after should be Q minus 1, and last will be the m, that's a multiplicand. And this is called as, this particular block is called as a process or action, which are being done as per your algorithm. So I'll name it as a process, or else I'll write it as an action. So this is an action which has been done according to my algorithm. So see now, A equal to all 4 zeros, and Q equal to, what is my Q? Q equal to 0 0 1 1. So Q equal to 0 0 1 1. And after that my Q minus 1. As I told, the initialization of Q minus 1 should be done to the 1-bit memory element. So that is initialized to 0. It is a Q minus 1 is a 1-bit memory. So it is initialized to only 0. First it should be initialized to 0. Then what is my multiplicand? Multiplicand equal to 0 1 1. So this is how I have done the initialization. Now let us go with the value of this, checking of this value. So see now, first, what is happening here? These two numbers only I should concentrate. Q and Q minus 1 I should concentrate. What is Q? Q equal to 1 and Q minus 1 equal to 0. So if it is 1 0, if it is 1 0, what I'll be doing? I'll be doing A minus 1. I'll be doing A minus 1. A minus 1 means I'll be doing A minus 1. A minus 1 means what? First for the 0, all the zeros is my accumulator, and minus M. A minus M I'll be doing. So what is M? M is equal to 0 triple 1 is there, 0 triple 1 is there, and this is my actually positive number, but here it has been written as a minus 1. I can even write this a minus 1 as a plus, I can write it as minus of m. Minus of m does not, it doesn't make any kind of change in the operation of subtraction. It is the same thing which you are written here. So, but how to get this minus m? So the minus m can be written as, minus m is nothing else but, in order to find out the minus m, you are supposed to do the 2's complement of that particular binary number. So how to do the 2's complement? If it is my 0, 0, 1, 1, and 1 is my binary number, first I'll be doing the 1's complement. 1's complement will be 1, 0, 0, and 0. For this 1's complement, I'll be adding the 1. If I add the 1, it becomes my 2's complement. So 1, 0, 0, and 1. So this will be my new value of minus m. This is the value of minus m. So now I'll be adding this minus m to this a value. What is the a value? Your a value is all zeros. If you add the m to the minus m, which is your new value is 1001, you will get the same answer again, 1001. If you add these two values, you get 1001. So this is what you get over here. See now, once if I add what we are doing here, that's now you can see now whenever it is 1 0, if it is 1 0 in the first cycle, what you are supposed to do, you should do a minus 1, and that value should be stored in the accumulator. So what is my new value now? A minus m value is 1001. That is stored here in this accumulator. That value is stored in the accumulator, and afterwards you write down all these values as whatever is similar to that one. 1100, the same thing will be written over here. The q minus 1 is again 0. Again m is equal to 1, 111. So we have added and we have stored that particular new value of a in the accumulator. After storing, what you are supposed to do, we know that as per the algorithm, whenever you do any kind of operation, the mandatory thing is that you are supposed to, after completing that operation, you are supposed to do the right shift operation, arithmetic right shift. You are supposed to do arithmetic right shift. In the arithmetic right shift, what you will be doing, the same thing. This number will be again written in the down, in the same position it will be written, and afterwards you can see whatever the number is there, the same number will be taken down. Then afterwards that number will be shifted to the right. So 1 comes over here, the 0 comes to this particular part, and this 0 comes over here, and this 1 comes to the next part, and afterwards 0, then 0, 1, and this 1 goes to this particular part. So now this will be my, after shifting, so see now, this is my particular new particular value. So you can see now this is my new value which I have got over here. So this is how we will be writing the data. After this one, you can see once if I do this one, after doing the shift arithmetic shift operation, what you'll be getting, you can see here now 1 state is there, 1 state. If it is 1 state, what is this 1 state? If it is 1 state, we know that in the 1 we will not be doing any kind of operation. You will be simply doing the right shift operation. So in the right shift operation means what? Again, you will be taking the, see, whatever I'm writing over here, assume it has an earlier there is no since I have put everything in a slide, you might get confused, but assume that there is a complete vacant all these are the vacant registers. Assume that one. So don't get confused. Before right shifting, all this was vacant registers. After shifting only, this particular data is visible to you. Think like that. So now it is 1 1. If it is 1 1, you'll be just doing the right shift operation. So if it is vacant here, means the first one will be taken down. It's only right shift operation. Why? Because it is 1 1 over here in the q and q minus 1. After this one is shifted to this particular part. That's why you got 1 over here in this location. After this one is shifted to this part, therefore you got 1 here, and this 0 is shifted to this location, so you got 0. After that, this 0 is shifted to the next q register, so therefore you have got 0 in this particular place. Then this 1 is shifted, and in this way simultaneously 0 and 0, and you can see this one from the q is now shifted to the 1-bit register, which is q minus 1. So now this is your new value of the accumulator. What is the new value of accumulator? The old value of accumulator is, in the first cycle, the new old value of the value of accumulator is 1110. But when it comes to the second cycle, the new value of accumulator is 1110. So this is how the value of accumulator is been changed. So now let us go for the checking of this q and q minus 1. What is this part? In the q and q minus 1, you are having 0 1. If it is 0 1, what you'll be doing? You'll be simply adding a plus m. You'll be simply adding a plus m, and you'll be whatever the answer you get, whatever the sum you get, that will be stored in an accumulator a. So what is my new value? What is the value of a over here? Value of a is now here is 111. It is 111, 1110. And what is the value of m? My m value is over here. It is 0 111. So it is 0. I'll be simply adding here. I'm not doing any kind of 2's complement. 2's complement is mainly done whenever you come across the negative terms. So see now, if I add what I get, 1 and 1 1 will be 0 and 1 carry. When it is 3 ones, it will be 1 and 1 carry will goes over here, and it's 1 1 over here, 0 and 1 will be carry, and this can be discarded. You can discard this one. So if you discard this particular carry, your sum will be 0 1 0 1. So this is your new accumulator value, which is obtained after doing a plus 1 operation. So you got 0 1 0 1. So that's why we have stored here. The accumulator value is 0 1 0 1. And simply after that, you'll be whatever the previous q value is there, that will be same as in the q register, and the previous q minus 1 will be there. It will be stored in the same place. Again, the m place will be same thing. There's the same value will be done. So now here we have done the a plus m operation. After doing this a plus operation, what you're supposed to do, once an operation has been completed, the mandatory thing is that right shifting has to be done. So assume now this complete block is empty. If it's empty, what happens? The 0 will be taken down. It will be same position. After that, the same 0 from that location will be shifted to the right, and 1 comes over here, 0 comes over here. Afterward, this 1 comes to this location of the what is that, q, and 0 moves to the next location of q, and 1 to the 1 to this location, and 0 to this location, and ultimately the 0 comes to this 1 bit register, which is q minus 1. So now this is your new value of accumulator. What is the new value of accumulator? Is this is your new value of accumulator. So see here now, what is the new after new value of accumulator is 0 0 1 0 is the new value of accumulator. After this operation, after a plus operation, my accumulator value was 0 1 0 1, but after doing the shift operation, my accumulator value is 0010. Now this shift is been done. Once the shift is been done, you should look for the possibilities of q and q minus 1. Check for the value of q and q minus 1. The q and q minus 1 is what? 0 0. If it is 0 0, what you will be doing? Simply you will be doing the shift operation. Why? Because we have studied that whenever it is 0 0 or 1 1, if it is 0 0 or 1 1, you will not be doing any kind of addition or subtraction. Instead, you will be just shifting the right shift operation. You will be doing only the right shift operation. So if it is 0 0, then what happens? Again, you should do the right shift for this accumulator, right from the accumulator. So see now, this 0 is been transferred to this location of the accumulator, new location of accumulator. So 0. After that, 0 comes to this particular location, then 0 moves to this location, 1 comes to this location, and then the last bit of this rightmost bit of the accumulator moves to the leftmost bit of the q register. So that's why 0 comes over here, and the q's leftmost bit moves to the next location, 1 and 0 0, and this will be my 1, and ultimately the 0 comes to this q bit. 0 comes to this q bit. Now we have completed the 4 cycles. Since it is a 4-bit number, we have completed the 4th cycle. So now you can say that you can wind up the operation of Booth algorithm, and you can check what is your answer for this particular Booth algorithm. So this will be your complete A and Q. 0 0, this is A, and Q, this is my 8-bit number. What I told, so see now, this will be a finally the if you put this a and cube next to each other, whatever the set of numbers you get, that will be your final answer, answer of your multiplication. You can cross check even. So what is my answer? I have written over here. Your answer is nothing else but 000101001. You can even cross check this one. What is this one? 2 power 0. 2 power 0 means what? 2 power 0 into 1, it is 1, plus 1 is in the location of 2 power 2, so it is 2 power 2 is equal to 4, and afterwards your location is what? 2 power 3, 2 power 4, 2 plus 2 power 4. What is 2 power 4? 2 power 4, it is 16, so it is 16,
21.
16, 4 is 20, plus 1, it's 21. What I told has as per this multiplication initially, as per the decimal number, 7 cross 3 is equal to 21. The same thing we have got in terms of your binary number. So this is how a Booth's algorithm is been used in order to do the multiplication of signed numbers and also unsigned numbers. If assume that if an unsigned number has been given to you, actually I thought of explaining you an unsigned number by using a board, but anyway the time has ended up over here. So I'll just try to give a glimpse of that one. If possible, in next class, we'll try to see unsigned number, how to do the multiplication of unsigned number by using the Booth algorithm. And this Booth algorithm multiplication is very important. And this is a part of the research which has been going on nowadays. You can, if you Google this one, Booth algorithm, you'll find some n number of research papers in Google or whatever may be the search engines. It's a very important what is that important research topic where it improves the number of it improves the speed of multiplication. Booth algorithm is mainly used for multiplying the unsigned numbers and also signed numbers, and also it improves the speed of the multiplication. That's the main important and advantages of the Booth algorithm. If you are trying to multiply 2 and minus 3, you are supposed to get minus 6. Then what you're supposed to do, the minus 3, you should convert it into 2's complement, and then only you can do all this process whatever we have just now seen. That is one way of doing the Booth algorithm with the minus minus kind of numbers, binary numbers. Or else there is another kind of method is also there where you will be using the recoded method. Recoded Booth method is there where you will be recoding that minus 3. After recoding, then whatever the value you get, that will be multiplied with the multiplicand. With the multiplicand, you will be recorded value of a multiplier. You will take it and you will multiply with the multiplicand, and then you'll fetch a product. That will be the final answer for your Booth algorithm. So there is again the two different ways are there in order to do one positive number and one negative number. We can do that one if possible in tomorrow's class. But as of now, the concept of your Booth algorithm has been done over here. So by this now we have completed the 4th unit contents. Yeah, please tell me.
Sir, here we have done with the hexadecimal values, no sir. If the terms are more than his hexadecimal number, is it valid or not?
So see, in hexadecimal number, again we are supposed to go for another method. The complexity will be increased. I'll explain that one. Why? Because what I told in the initial of this particular class, if you are trying to multiply n number bit of numbers, then the number of iterations will be that many. If you are trying to do the multiplication of 4-bit numbers, iterations is 4 only. That's why we are used over here 4 cycles. If you are trying to multiply 8-bit numbers, then iterations will be 8. If you are going to do 15-bit number, where the hexadecimal is going to start, is it okay? Then you are supposed to think about the 15 iterations. Have you got my point or not?
Yes,
the complexity is going to increase. Then again, the methods we are supposed to use, again what I told, what is that one, recoded method can be used. And one important point is that Booth algorithm, if you are trying to attempt your gate paper, definitely you can expect one question from the Booth algorithm with respect to recoded method. What I told in the up now I told about recoded method, right? In the recoded method, they might ask you a question: how many number of sum and how many number of negative and positive numbers are there? They'll ask in that particular way. That is one of the gate question can be we can expect that kind of gate question from the Booth algorithm. We'll try to see, if possible, we'll try to see it in the tomorrow's class, or else directly we'll enter to the new topic. Okay. I hope you all have understood the Booth algorithm very clearly. Is there any doubts? You can ask me now.
Sir, here for the 4 iterations, at first we have taken A minus M. In the second iteration, it is shift, that is 1 0 1 1. They will be constant, sir, always.
For any, see, for the Booth algorithm, you're supposed to remember the algorithm first.
Sir.
Algorithm, what is the algorithm? Algorithm, it tells that if my Q and Q naught is 1 1 or 0 0, I'll not be doing any kind of operation. I'll be just shifting the right shift. I'll be doing arithmetic